In this video, we'll find out why we need activation layer in neural network, and then we'll see different types of activation layers like Sigmoid, Tanh, ReLU, Leaky, Softmax, etc. Few of the activation layers we have already seen in our previous videos like Sigmoid and Softmax. We'll see the rest of them. We'll also see when to use which type of activation functions. In the previous video, I discussed why we need neural networks and why traditional machine learning models are not enough for our real world problems. And we saw why we need hidden layers in neural network. We saw if a small function like XOR function cannot be represented in a neural network without hidden layers. So we added one hidden layer with two nodes H1 and H2, and then we came up with a neural network like this. This H1 behaved like a OR function, H2 behaved like an AND function, and then Y was a combination of H1, H2, V1, V2. This behaved like a XOR function. So if you want to see the detailed descriptions, you can see my previous video. I can give the link also here. Now, without this sigmoids, can we model XOR function? Is it possible? So let's see why not. So let's say we don't have the sigmoids. So these are the weights here. So let's represent H1 with those weights, and also let's introduce some bias here, B1 with weight W01, and here we are getting a bias B2 with W02. So H1 can be represented as W01 plus W11x1 plus W21x2. H2 can be represented as W02 plus W12x1, W22x2. And Y is, let's say we have one bias for Y as well here with weight V0 here. So Y is V0 plus V1H1 plus V2H2. So let's replace this H1 and H2 here. So we get V0 plus V1, this thing here, plus V2 H2 here. Now let's simplify this. V0 plus V1 W01 plus V2 W02. So these three are the three biases. Then we get V1 W11x1, and here we have V2 W12x1. So we can write it as V1 W11 plus V2 W12, and we can multiply this with x1. And here we get V1 W12 plus V2 W22 times x2. So if we say this thing, if we do the summation, and this is W0, this is capital W1, and this is capital W2. So this is like this, we can write it, this is W0 plus W1x1 plus W2x2. So this is still a linear combination. So the combinations of all these linear equations are always linear, right? So we added linear equation here, we added linear equation here, and then we added one more. This Y was a linear combination of H1 and H2. But ultimately we got one linear combination of again, right? So doesn't matter how many hidden layers we add, our output will be still a linear equation. But if you see the XOR function, the decision boundary is not linearly separable. So for 0, 0 we have 0, for 1, 1 we have 1, 0, right? So we cannot draw any line to separate zeros and ones. So with a linear equation like this, we cannot solve a function like XOR. So that's why we have introduced some non-linearity. So here sigmoid acted as a non-linearity function. Now see a few examples here about linearly separable and not separable scenarios. So we are talking about two classes, right? So in this case, two classes can be linearly separable nicely. Here in this case, the decision boundary is not linearly separable. Here also, the boundary is not separable, linearly separable. So most real world problems deal with non-linear data. So consider about image classification. Recognizing a cat in an image requires understanding curves, textures, shapes, and spatial relationships, all inherently non-linear patterns. Natural language processing. So understanding and classifying human language, sentiment analysis, spam detection, translation, all this involves non-linear relationships between words and context. In recommendation systems, predicting user preferences for products, movies, or music involves highly non-linear interactions between user history, item features, and context. In case of speech recognition, so the audio data contains complex patterns that vary greatly, so requiring non-linear models to interpret human speech accurately. Autonomous driving. So data used for object detection and decision making is in self-driving cars. So it distinguishing pedestrians from vehicles in real-time video feeds. This is one example, right? So in a real-time video feeds, if we can distinguish pedestrians from vehicles. So all these data are inherently non-linear. So our without non-linearity, we won't be able to solve this type of complex problems. Now next we'll see different types of activation functions. So first we'll start with sigmoid that we have already seen in our logistic regression video. So the formula is fx equals to 1 over 1 plus e power minus x, and the function it runs from 0 to 1. The value is from 0 to 1. So that's why it is used for probability calculation. So when x is 0, the fx value is 0.5. Where it is used? It is used in output layer of binary classification. It's used for probability output 0 to 1. Why it is used? Because output can be interpreted as probabilities. And this is very smooth function and differentiable. In the logistic regression video, we also saw how to find out the derivative of sigmoid. Few limitations. First one is vanishing gradient. So vanishing gradient is an important topic. So I will create a separate video for vanishing gradient. But I'll just to give the idea. So to train the model, we use gradient descent, right? And so gradient descent loss curves will look like this. So we'll calculate the gradient. If it is positive gradient, we move in this negative direction. If it is negative gradient, then you move in the positive direction. Our goal is to reach in the minimum position. So in vanishing gradient, so gradient becomes very small, tends to 0, right? And then that's why if gradient value becomes very small, then model will not learn. So will not converge. So that is a problem of vanishing gradient, but I will discuss why it happens in neural networks in a separate video. So next limitation of sigmoid is it is not zero center. So for x equals to 0, the value is 0.5. And it has slow training in deep networks. So in a deep network, we cannot use sigmoid. Next function is hyperbolic tangent. So the formula is fx equals to ex minus e power minus x over e power x plus e power minus x. So the function runs from minus 1 to 1. Sigmoid runs from 0 to 1, but tanh runs from minus 1 to 1. And the mid value, at 0, the fx value is 0. So this is a zero-centered function. So where it is used in hidden layers, older neural networks. So basically earlier we used to use this Tanh functions a lot. Nowadays in RNNs and LSTMs we use Tanh. So RNN is recurrent neural network and LSTM long short-term memories. So these things we'll discuss later in separate playlist, and then we'll clearly discuss why we use Tanh there. But this is one simple example, like when output needs to be between -1 to +1. If this type of requirements is there, then we can use Tanh. Why we use Tanh? This is a zero-centered output if our requirement is like that, so we can use Tanh. And it has stronger gradient than Sigmoid. So stronger gradient as in the slope can be steeper than Sigmoid. Now, few limitations, it still suffers from vanishing gradient and it is slower than ReLU. So, ReLU is the most commonly used activation function. So, we'll see it next now. But Tanh is slower than ReLU. So, that's why ReLU somehow replaced Tanh. So, this is ReLU or rectified linear unit. So, this is very simple. Fx is max of 0 or x. So, if x value is positive, it is fx is x. If it is negative, it is 0. It's very simple. So, where it is used? In hidden layers of deep neural networks, in computer vision tasks, and in most modern deep learning models as a hidden layer, as an activation function for the hidden layers, we use ReLU. Why we use fast computation? It's just a max of the 0 and x, right? So this is a very fast computation. No vanishing gradient for x greater than 0. So for x greater than 0, this is activation function is just not changing anything, right? It's just fx equals to x. So we don't see vanishing gradient for x greater than 0. Sparse activation. So you see many values will be 0, right? For negative x it will be 0. So many of the activation will result into 0 values, and in that case the complex models will become simpler, right? So it helps in fighting overfitting. That's why. Limitations. So though ReLU helps in solving this vanishing gradient problem, we have a dying ReLU problem that also we'll discuss later. So what happens is this neuron stuck at 0. So this is a dying ReLU problem, but this happens for very complex networks. So to solve this, we have a Leaky ReLU function. So Leaky ReLU is same when x is positive, fx is x, if x is greater than 0. But when x was negative, earlier it was 0, but here it is beta x, if x less than equals to 0. Usually, the beta values lies between 0.01 to 0.3. So this is just we get small values for negative x's. Where it is used? In hidden layers when ReLU fails, in GANs like generative adversarial networks. That these are complex topics we'll discuss much later. Deep CNNs like this CNN is convolutional neural network in computer vision. So in deep CNNs with dying ReLU issue we use Leaky ReLU. Why it is used? It prevents neurons from dying. So there is this dying ReLU problem, right? It solves that. And small gradient for negative outputs. If we want small gradient for negative output in this type of problems, we can use Leaky ReLU. So our approach should be we should use ReLU for hidden layers, but if ReLU fails, we can go for Leaky ReLU. Limitations is slightly slower than ReLU, and this beta is a hyperparameter. And the next one is Softmax. Softmax we have seen in multi-class classification, we used Softmax. So consider Z1, Z2, Zk, these are the classes, right? And Softmax of any Zi will be e power Zi over summation of all u power Zj. right? So this gives the probabilities for all the classes, and these probabilities will sum up to 1. So here we have one scenario with binary classification. So if we used sigmoid, we used to get only one probability, right? So here, just because we have multiple classes, we'll get multiple probabilities. So I'm just showing for two classes here. So this is class 1 probability, this is class 2 probability. So at any point, the summation of these two probabilities will be 1. So where it is used in output layer of multi-class classification. So that we have already seen our multi-class classification video. And final layers in CNN or convolutional neural network. In transformer architecture, we use Softmax. Why it is used? It converts scores into probabilities. We need the probabilities for multiple classes, right? So that's why we use it. And it is differentiable, so we can use it. So here we have one more example with 3 class. So this is for class 1, this is for class 2, let's say, and this is for class 3, right? So here also these are probabilities for 3 classes, but at any point you see, if you sum them up, sum the probabilities, will get 1. So few limitations of softmax is it's only for mutually exclusive classes, right? One point data point sample belongs to only one class, right? So those kind of mutually exclusive classes, we can use softmax. It is sensitive to large values, right? Because this exponential, this can overflow. It's not suitable for hidden layers. So softmax no one uses for hidden layers. Softmax is for output layers for probability calculation. So vanishing gradients when one class dominates. So if one class dominates for the other classes, we can see vanishing gradient.